I hope reading week went well. We're now about to begin the second half of the module Geometric Topology, and the main theme will be the study of surfaces. I want to classify surfaces, and this will take at least 2 or maybe a bit more weeks to do. It will be the main theorem really in the second half of the course, and then we'll be doing various examples and consequences of that. So you should try and watch this first video before the live lecture if you're able to, especially if your live lecture is on campus on Tuesday. I'm going to explain the classification theorem. I already explained it in the introductory lecture, the second introductory lecture. So please watch that if you haven't done so, but I'll be a bit more precise in this talk. So the thing about surfaces, what are we talking about? Technically we're talking about connected, that just means there's one piece. Compact surfaces, that means somehow they're limited, they're not infinite. And we don't want any boundaries. Later on we will be talking about surfaces with boundaries because the boundaries may well be a knot if there's just one boundary component. But for the first part of this section, half really of the module, we're going to talk about surfaces without boundary. These are sometimes called closed surfaces, to say that there's no boundary, but not closed quite in the topological sense. So as I explained before, there are really 2 families of these surfaces. There are the orientable ones. They're very easy to imagine. There's the sphere, there's the torus. That's, you think of the torus as a sort of donut with one hole. And then you can sort of put more holes in and get tori with various holes. And so it's quite easy to imagine those in ordinary space. And then there's a whole family of non-orientable surfaces, which you can't easily imagine in space. So we'll be talking about these. So bear in mind that there are these 2 types, orientable and non-orientable surfaces. So first of all, let me give you a sort of correct definition. So a surface without boundary is really the same as a 2-manifold. If you're at level 7 and doing the course on manifolds, topologically it's like a 2-manifold. And it's simply a topological space, each point of which looks like Euclidean space. In this case it's 2-dimensional, so it looks like the Euclidean plane. Technically that means that around each point you can find a neighbourhood, an open set, which is homeomorphic to a disk in the plane. So a disk means the usual interior of the interior of a usual circle, a round circle. So that would be a disk, and you just want that each point of your manifold has an open set that's homeomorphic to such a disk. So it may have a funny looking boundary, but it's got to be homeomorphic, topologically equivalent to a disk. That's what a surface is. Now, technically, we have to add this word Hausdorff. So if you've done metric spaces and topology and you know what Hausdorff means, that's fine. It's just a technical condition that's added to prevent some rather nasty looking objects. But if you don't know what Hausdorff means, you can sort of forget it, to be honest. In my first draft, I didn't even put it in, but then someone would complain. So that's what a surface is, technically speaking. So it has this locally Euclidean property. That's the point, that each point looks like the Euclidean plane. And here are some images of surfaces. These are all sort of visible in R3. So these would all be orientable surfaces, except the last one is not a surface. The last one is not a surface because it doesn't have this property that around each point it looks like the plane, because if we take these are so-called singular points here, and you can see they don't really look like the plane. Let's take a point here where these sort of link, where these sort of sausages are joining. That's really looks like 2 planes stuck together. If I removed one of these sausages, then it would actually this point would be fine. It doesn't matter the fact it's sharp, because we're not talking about differentiable stuff. We're talking about topologically continuous functions. So if I just took this point here without this second sausage, that would be locally Euclidean. But the fact these sausages are joined together stops it being a surface. The others are surfaces, so provided you don't look too carefully at the purple one, where the sort of pits are joined. If you look from a distance, it's really what I would call a torus with 3 holes. And the first two are just simple tori. Now, you might think the second one is not so simple, but the fact is, when we're talking, we're not, in this part of the course, we're talking about homeomorphism. We want to classify surfaces up to topological equivalence. We don't care how they're sort of sitting inside space. It's just for convenience that we see them in space. But the torus you can think about entirely abstractly, as I'll show you on the next slide. You don't have to imagine the torus as embedded in ordinary space. And in fact, the second image here is the same object topologically, it's just embedded differently. It's embedded as a sort of trefoil, sort of tube around a trefoil knot. But that's not relevant anymore. We're not going to talk about isotopy classes. These two surfaces, you could say, are not isotopic in the sense that one cannot be deformed to the other in space, but they are nonetheless homeomorphic, just as 2 knots are homeomorphic. 2 knots, however complicated one is, the other may be an unknot, they're still homeomorphic because they're both homeomorphic to a circle. Okay, so in the same way, these two surfaces are homeomorphic, so we regard them as the same. They are just a torus. I'll be using the letter capital T to denote any surface which is homeomorphic to a torus, if you like the first one. So that's the idea in the sort of zoo of surfaces, although here you're not seeing any of the non-orientable ones. Now, let me be a bit more abstract now. So I'm going to talk about 4 particular surfaces defined in a more abstract way. So the idea is, if you're given a surface like the ones we've just seen, if you start, pretend they're made of paper or something, the first thing to emphasize is they're surfaces. There's no inside. They're not solid in any way. We're just looking at the surfaces. So you should think about balloons. You know, think about this second one as a sort of party balloon, although it'd be quite difficult to manufacture it because it's closed. But we're just talking about there's air inside. There's nothing inside. They're surfaces. So if we cut them up, we'll go back once again, if you sort of cut them up into small enough pieces, you can sort of flatten them out topologically and put them on the plane and then examine how they've been stuck together. And that would be one sort of a first approach to classifying them. So let me explain this point of view for 4 very simple surfaces in which you can just represent them really by squares. So here goes. This is fairly well known and I hope it might be familiar to you. So, for example, the first square represents, with the sort of edges and arrows, it represents the torus, the first image, if you like, that we saw. Or equivalently, the second image, because they're both topologically tori. So, just look at the first square for the moment. Notice that the arrows are sort of consistent. They're parallel, oriented in a sort of parallel sense. So you see the first square, this may be obvious to you, but nonetheless, let me explain it. So if you just take the first square, the red arrows are telling you, that's the arrows top and bottom, are telling you they're to be sort of stuck together. So that as it stands, the square has a boundary, of course, but we don't want our surface to have a boundary. So we've got to make sure there's no boundary left. And in order to ensure that, we have to join opposite edges, in this case, opposite edges. That will ensure that, for example, if you have an insect living on this surface, so the surface includes the inside, of course, you have an insect crawling about on the inside. If the insect crawls towards this boundary here, the insect doesn't actually see the boundary because it comes straight out at the bottom and it can just go round and round and round. Or if it then decides to go off to the right, to that blue boundary, then it will just come out the other side, because the boundaries have been identified in that way. And if you first of all stick the top and bottom boundaries together, you get a cylinder. At least if you start with a rectangle rather than a square, you get a cylinder in which you just glue top to bottom. That's pretty obvious. But then if you want to glue the blue ends together, you're going to get a torus. I can't really show you here because paper is too rigid, but here I've sort of got the blue. You can still see the blue edges, and with the arrows being consistent, I could just, if it were made of rubber, I could just join it together and I'd get the torus. So that's the model of the torus. Now, if we now look at the second square, it's almost the same. The top and bottom arrows are both consistent, but this time if our insect sort of crawls out down the bottom here to the blue edge, it will come out at the top here, because the blue edges left and right have been identified in the opposite way. And in this case we get something which you may know about. It's called the Klein bottle. So it's like taking the cylinder, but in order to match the blue edges up now, you can't just do that. You have to actually, one way of doing it would be to pass the cylinder through itself and then do the matching. I can't show you with paper. Okay, so that is the Klein bottle, and that's an example. That's our first example of a non-orientable surface. It can't be visualized in space without self-intersection. There will be points in space in which a single point in space actually represents 2 points on the surface. I'll show you a picture in a moment. Then we go even further in the third image, because here I've reversed both pairs of arrows. So in this case, we have both top and bottom and left and right are sort of oriented differently. So again, if our insect crawls in this point there, it will come out at the bottom on the right hand side. And that's another non-orientable surface. It's called the projective plane. Strictly speaking, it's called the real projective plane, because there is inevitably a complex projective plane. That's much more complicated. If you do level 7 algebraic geometry next semester, you'll know all about complex projective spaces. And then the last example, sigh of relief, is much simpler to understand. It's just a sphere. Why is it a sphere? Because the arrows, although I've got sort of 4 arrows in this square, I don't really need the square, because I could actually think about putting these 2 arrows together as a single arrow, top right and bottom left, and make these single arrows and identify them. And you begin to see, if you do that identification, you're just closing the surface up and it just does become a sphere. These 2 points I put in green because in this example these 2 points are distinct, whereas in all the other images points are identified. So for example, in the first example, these 4 points are all the same. By the time you've glued it together, you've glued your cylinder together and stuck it all together, you'll see that all these 4 points, 2 have already come together they've come together in pairs when I do the cylinder. When I put the ends together, they're all the same point. In the case of, and then you can ask what happens in the other cases. The Klein bottle, they're all the same point. The projective plane, there are really 2 points. There are the blue and blue is 1 point and red is 1 point. Whereas for the sphere, there are 3 separate points. 3 points. These 2 points will get identified when I glue this arrow to this arrow. So there are 3 distinct points rather than 4. Okay, so these are the sort of square models. Now we're going to generalize this to look at much more complicated surfaces. So instead of squares, we're going to have polygons. And that will lead us to sort of prove the classification of surfaces, or establish the classification of surfaces. And we're going to do this in a sort of fairly algebraic or combinatorial way, because diagrams are very helpful to begin with, but I don't want to have to draw diagrams all the time because it takes a lot of effort, particularly on screen. So we're going to use these sort of letters and words to understand how our boundaries are treated. So in the case of the squares, you see, we can actually label the edges, the boundary edges, by letters. So let's go back to the first example of the torus, I normally I prefer to go clockwise. Some people go anti-clockwise, but so I'm going to call this first edge A, and then this one B, and then you see the bottom edge is the same as the top edge, so it's going to be called A again, and the left edge is the same as the right edge. But look at the arrows, look at the direction of the arrows. If we go round clockwise, you see, if I want to take account of the arrows, I'm going to use inverse signs. So A and B are going in the correct direction clockwise, but when I come to the second A and the second B, bottom A and left B, they're sort of going against they're going anti-clockwise. So I record those with inverses. So I can encode this sort of boundary, the boundary identifications by the word, we call this a word, AB, A inverse, B inverse. And I can do that for the other four models. Here we have A, B, A inverse, B. Here we have A, B, A, B. In a certain sense, that's the simplest in terms of the word. It's the projective plane. It's probably the most complicated of these four surfaces to visualize, but it's the simplest to write down in terms of this boundary identification. It's just A, B, A, B. Actually, here again, you could just use two arrows because I could combine the red arrow and the blue arrow and just call that just a sort of single arrow here, as I did for the sphere. But then the other problem is that the arrow going the other way, so it's going in the same direction, unlike the sphere. So again, I could just use two arrows, but they'd have to be, they're sort of identified in the opposite direction. This is clockwise and this is anti-clockwise. So if I do that, I could just write sort of, for this surface, I could write maybe capital A, AA. I could use AA to represent this surface. Whereas the sphere, I could sort of write this as capital A inverse if I use the single arrows as I did before, both going. So one would be clockwise and one would be anti-clockwise. Okay, so that's the sort of idea of what we're going to do, but in a more complicated fashion, because in a moment being in a day or two, we're going to start looking at polygons. So let's now look at some pictures, and here it's a bit more difficult really. Well, the sphere is the easiest one because the sphere, remember, you could just think of it really as a disk. If I just use my two arrows, then I'm really thinking of it as I can sort of think about, instead of the square becomes a sort of round disk, and I can think of this disk as really the sort of part of a sphere. If I push it down, then I get a sort of bag. I put the arrows the wrong way. Sorry for the sphere, that was a mistake. Because for the sphere, the arrows are both going, one is going clockwise and one is going anti-clockwise. And that, you can think of this as just a zipper. You just zip up the bag in the usual way. And then, of course, if you zip up the bag, you get the sphere. So that's easy enough. The Klein bottle there's a visualization you can actually buy Klein bottles. So here you see that really I started with a cylinder in a sense, and I had to bring the cylinder inside itself to get the identification of the blue edges done properly here. So if you look at what happens there, no, sorry, not there. That's where the boundary of the cylinder, the boundaries of the cylinder are joined together. That's perfectly fine, but it's this circle here is where the surface passes through itself, where the cylinder passes through itself. So any point of this circle here, of the handle, although it's 1 point in R3, it's actually 2 points on the surface abstract. Now the projective plane is more complicated, and to sort of understand this, I'm going to start with this first sort of picture here. So this is really remember I said for the projective plane you don't need the square, you could just put sort of two arrows. So that would already make it sort of into a disk. But this time the arrows, remember, both go clockwise. So, we have these two edges here, these two edges which we saw before in the square, but are both going clockwise. So the sort of code for the boundary is sort of capital A, capital A. Now, how do how do you visualize that? It's very difficult. What you can do is you can try and sort of pull these edges up like this and to try and close the sphere down. But the problem is, if you look at the identifications, you've got to identify, I've now sort of gone back to 4 separate edges if I divide them there. And this sort of edge here has got to be identified with this edge here. So although now I've got the arrows sort of going together, and this edge here has to be identified with this edge here, but in order to do those identifications, you have to sort of pull the surface. I mean, although I've pulled the surface up, so this is now sort of part of the surface, you then have to sort of pull the surface through itself. It's quite hard to imagine that, but the picture in the top right shows you what's going on. You get sort of figures of 8 as you pull the surface through itself and do these, so that these sort of 4 edges, which were the 4 edges of my square, they really correspond, they're being identified, and they correspond to this part of the surface now visualized in R3. But I had 4 edges, I'm identifying them in pairs, that reduces me to 2 edges. So there are 2 edges on the surface here, but there's only 1 edge in R3. So again, you're seeing the surface cut through itself, it's self-intersecting. I've cut it away a bit, it would be closed up here, but I've cut it away to show you what's going on. And that picture, that's called a cross cap. This part of the surface is called a cross cap. This identification that really sort of converts a sphere into the projective plane. So that's one way of visualizing the projective plane. There are other ways, actually. Study of how to put the projective plane in space is a big subject in itself. But this is the sort of most common way of understanding, of visualizing the projective plane. So last comment here. So we have the Klein bottle. So the Klein bottle, you see, it has this circle of self-intersection, which is fairly well behaved, whereas the projective plane is a bit more awkward because it has a sort of segment of self-intersection and there's all singular points at both ends of this segment. Okay, so I also meant to remind you here that I did talk about the projective plane in the first lecture, the very first lecture of this course. If you go back to the slides for that, you can see there's one on the projective plane, and I explain there why this object really does correspond to lines through the origin in R3. Because that's the definition of a projective plane or space. It's a set of one-dimensional subspaces in some vector space. In this case, it's a set of one-dimensional subspaces in R3. And again, just to emphasize that we're talking about the real projective plane here, so some people use that notation. Okay, now I need to talk about the classification theorem. This is working out a bit longer than I expected. I'm sorry, but I'll whip through this. So here is another way of writing down well, I've already mentioned this before in my second introductory lecture, but here is a sort of informal way of explaining the classification theorem of surfaces without boundary. So technically connected compact surfaces. So each such surface is topologically equivalent to one of the following. So don't let this word homeomorphism frighten you. Sorry, I was meant to hide that cross cap. Homeomorphic to just means topologically equivalent to. So any such surface is either the sphere, we've seen models for the sphere, or it's a sphere with a certain number of handles. Well, that's really the same thing as a donut with a certain number of holes. Because a sphere with a handle, you think of a sort of mug. So just think of the surface here. So you can pretend the mug is a sphere. And I've just put a sort of tube added to it. This tube is meant to be empty, air inside, not solid. So that would be a handle. And that's really topologically equivalent just to a torus, because I could sort of, the sphere could be sort of pushed down and I can make this completely symmetric, so it's just a torus. So you can get these sort of, when you talk about torus with a certain number of holes, you're really just putting handles, putting tubes on a sphere. So, and you can put 1 or 2 or 3 and so on. So you've got an infinite number of such surfaces which are obviously not equivalent. So those are the orientable surfaces, full stop. The difficulty is, what about the non-orientable surfaces? Well, it turns out all you have to do is start with a sphere and add 1 or more of these cross caps, which you can do sort of near each point. You can sort of do this operation I told you about. You sort of cut out a little disk and pull the edges up and do this identification in which there are self-intersections. And you get these, you get cross caps. You need at least 1, otherwise you just have the sphere, which you can think of as a sphere with 0 handles. So G is equal to 0. G is called the genus, and you can have G is equal to 0. That just gives you the sphere. But to get something non-orientable, you need at least 1 cross cap. It turns out, you might say, what about the Klein bottle? Well, the Klein bottle is actually a sphere with 2 cross caps. It's not obvious, but it's quite easy to show. We'll do that very soon. So that is that's really the classification of surfaces. Let's just show you the picture of the cross cap again. So those are the things you have to add to. There's a sphere with 1 cross cap, which is itself the real projective plane. If you add 2 of those cross caps, you can make the second one smaller, maybe, and sort of arrange it around here. Then you get the Klein. You get something which is equivalent, can be deformed, or homeomorphic to the Klein bottle. So in the first case, we're talking about the orientable surfaces, and those are the ones you can visualize directly in R3. That is, there's a continuous one-to-one map of the surface into 3 space, if you want to visualize it. And they're called orientable. You can assign a sort of consistent sense of rotating by 90 degrees. This orientable means you've got a consistent notion of sort of clockwise and anti-clockwise near each point on the surface. I'll explain that later on. And the non-orientable surfaces are, okay, well, the other thing to say is that when I talk about a sort of torus with G holes, you can also think about that as getting that by taking one torus, sticking another next to it, and sort of gluing them together, and you can glue any number of tori on. And that operation is like we did for knots when we talked about composite knots, the granny knot and so on. And it's the notion of connected sum, connect sum. So you can do that for toruses, so you can do that for surfaces. So for example, in case 1, we're just saying any orientable surface is a connect sum of a number of tori. And what about the non-orientable surfaces? Well, I've explained that already. You just take a number of cross caps, or that's the same thing as saying you stick together a number of these projective planes and glue them together. And the Klein bottle corresponds to 2 of those. Okay, that's it for the first part. In the live lecture, I'll be explaining in more detail what we have to do to classify these surfaces using these sort of identification of boundary edges.